Okay, so what we're looking at here, or trying to figure out, is basically uncertainty and error propagation. So just to set up here, we found a leaky tap, and we put our graduated cylinder under the tap for 20 seconds, and then we took a picture of the results. So this is how much water we leaked from our tap into our graduated cylinder in 20 seconds. So the first thing we need to do is agree on what this reads, all right? So we measure on a graduated cylinder from the bottom of the meniscus, which a meniscus is just the curvature of the water, and it's due to surface tension. So the agreed upon method for reading something like this is to read from the bottom there. So if you look, to me, we're looking right here, okay? So somewhere between this line and this line. This line right here is our 16 mil mark. This line here is our 15 mil mark. Okay? There's 1, 2, 3, 4, 5 gradations between there, so 15.2, 0.4, 0.6, 0.8, and 16. So we can agree, I think, that we're somewhere between 15.8 on the low side and 16.0 on the high side. So the question is, what do we do with that? Well, what we have to do is estimate roughly how far between these two gradations on here we're at, and come to an agreement on what the actual value of that reading is. So what we need to do then is we need to estimate this last digit. I think a pretty reasonable estimation, from me looking at it, puts it at probably 15.9, I'm thinking. So 15.9 milliliters. Now the problem with that is we're sort of like having to estimate this last digit. That last digit is estimated by us. Okay? So what that means is it's going to carry some uncertainty. All right? So uncertainty just means we know it's in this range somewhere, and we're putting this last value here. We're using it. We're using an estimated digit for that last value. So how we deal with that uncertainty is when we write our value down, we write our uncertainty as plus or minus half the last readable digit. Readable digit. Last readable digit just means the most precise digit available to us on an analog tool. These gradations are each 0.2 mils apart. So half our last readable digit then will always be 0.1 mil, plus or minus 0.1 milliliter. So what we're going to write this down then as is 15.9 plus or minus 0.1 milliliters. You see that agrees with exactly what we've read off here. 15.9 plus 0.1 is 16, and minus 0.1 is 15.8. So it's perfect, right? We're saying that there's a range of values it could fall in. We've estimated that. We just know that it's somewhere within here. So the second part of sorting out this problem, which again is going to be how much it's going to cost us in 1 year to pay for that dripping tap, is time. All right, so now I was a little probably sloppy in this measurement because I read it off the clock, but we got from our standard wall clock in the classroom, this took 20 seconds. But there's going to be some uncertainty on that reading, isn't there? So we have to decide what the uncertainty on that reading is. Okay, so the wall clock is marked out to the nearest minute. All right, or sorry, that's actually not correct. These represent seconds as our second hand moves around, right? So if we're reading 20 seconds here, say we started timing there and we ended timing here. and we read 20 seconds. 5, 10, actually that's not enough. That's only 10. We stopped reading here, sorry. How would we actually end up writing down our 20 seconds? Plus or minus how many seconds? So we have, reading from the third hand here, or the seconds hand, we see that there is 60 seconds around the entire clock, right? 5 times 12, so 60 seconds. So in other words, the smallest value we can read using the red hand here is 1 second. So the precision of the clock is 1 second intervals. So what that means then is that the uncertainty in our time is plus or minus 0.5 seconds. The reason being is if we look, say, at this hand right here where it is, I mean, it doesn't tie into what we're doing, but where it is on here, if I just extend it out a little bit, we'll see that it points right in between 2 seconds. So we would probably read this as, let's see here, 5, 10, 15, 20, 25, 30, 35, 36. So between 36 and 37, we're going to estimate that value. So where this is pointing right now is at 36 seconds. But I'm going to say it's between 36 and 37. So I'm going to call it 36.5, right? If I read it there, 36.5, but plus or minus 0.5 seconds. So in other words, we see that it's somewhere between 37 on the high side and 36 on the low side, and that exactly agrees with what we're talking about. Now, another person might come along, and they might read it as 30 seconds, 36.6. But that uncertainty will cover that range, and really, unless there's something wrong with the way that you tell time, no matter who in this room takes a look at that clock, you're all going to come up with some value here, which is between 36 and 37. So by putting that range of uncertainty on there, we're all, as different scientists, going to come to the same conclusion, and we're all going to be accurate within some range of allowed values, okay? So the accuracy across the room, unless you don't know how to use a clock, is going to be the same, right? We're all going to come up with an accurate value, okay? So our actual measurement that we took, we watched for 20 seconds, but we know from our clock that that's 20 seconds plus or minus 0.5 seconds. Okay, so now we're going to take this information and we're going to come up with a rate of dripping for that tap. But that rate of dripping has two inputs for finding it, and each of those carry uncertainty. Now, great question from the audience here, and that question is this. So what we're dealing with here is basically a time interval. And that time interval has a start time and an end time, right? So we started measuring right here, which is 0 plus or minus 0.5 seconds. And we ended over here at 20 plus or minus 0.5 seconds. And what we're actually looking at is a delta t, okay? So a final time here and an initial time here. So we have to account actually for that, the fact that there's uncertainty of where we started. Okay. You wouldn't run into this if you were, say, if you were using like a stopwatch and you clicked it on. You would just take that the start time, the absolute value of the start time is 0, or if you were reading like a thermometer and you just wanted the actual temperature right now. But when you're dealing with an interval, you have to understand, yeah, that's correct, that there is uncertainty on both ends of it. So what you'd get then is you'd get 20 plus or minus 0.5, subtract 0 plus or minus 0.5. And that might seem like a weird thing to do because you're just going to get 20. But what will actually happen when you're adding two things with uncertainty, you are going to, or subtracting two things with uncertainty on them, is you're going to actually end up adding the absolute uncertainties together. So 20 plus or minus 0, no, yeah. because you have to go 0.5 plus 0.5 seconds. You have to add the uncertainties together. So we actually get plus or minus 1 second. Thanks for that. That's a great point. Okay. Okay, so now what we want to do is we want to sort out what is the rate of drip per second. This is where it gets a little more complicated. All right. So we had 15.9 plus or minus 0.1 milliliter every 20 plus or minus 1 second. All right. So a few things are going to come into play here. The first is significant digits. All right. So when I look at this looks to me like it only has one significant digit. Is that true though? Is there only one significant digit here? Or is this actually a significant digit as well? Like, do we know it to the nearest 1 second or not? Yeah, we do, right? So this actually has two significant digits, even though this happens to be a 0. So what's a better way to write this so that if someone reading it knows there's two significant digits there? Yeah. Exactly. Okay. So to make sure that the person reading this knows that we know that value, we have to resort to scientific notation. Now that says, because every digit we write in scientific notation is significant. All right. So the way to get around that, having a state to two significant digits is to write it like that. So the first step then, actually, when we're doing a division or a multiplication, is we have to go from what's called absolute uncertainty to relative uncertainty. In other words, we have to convert this to a percentage of the whole value. All right, so a percentage of the whole value. So before we can actually go through with this problem or dealing with the uncertainty, we need to know what the percentage uncertainty on each of these values is. So for 15.9, we go 0.1 milliliters of the 15.9 milliliters is uncertain. So times 100%. And you don't necessarily have to go all the way to percentage. You can just leave it as a decimal uncertainty. But I think I prefer to have it as a percentage. And then the percentage uncertainty on your time is 1 second out of my 20 seconds is uncertain. Okay, so we've just run out of time. We'll continue where we left off next time. And okay, so continuing our propagation of uncertainty that we did last time. 15.9 milliliters of water plus or minus 0.1 mil. Right, because this is a 0.1 mil because our graduated cylinder is in 2 mil increments, or 0.2 mil increments, sorry. So what we did was we calculated the percent uncertainty on each of these values, and then what you'll do is you'll find the sum of those values. So when we get the drip rate, it's going to have 5.6% uncertainty on it. So the sum of the input uncertainties as relative uncertainties is the uncertainty in the value we get for drip rate. So our 0.795, because we have 2 sig figs, rounds to 0.80, plus or minus 5.6%. Okay. Our percentage uncertainty should have the same number of digits, or the same number of sig figs, I should say, as our actual value does. So 2 there, 2 there. So what we'll do now is we'll just convert that to an absolute value. So 0.80 plus or minus 5.6% mils per second. And we want to go back to an absolute value for that. So 0.80 times 5.6 100ths. And this is going to give us the amount of absolute uncertainty on that value. 0.0448. Okay, so that's plus or minus that amount. So we would now write this as 0.80 plus or minus 0.0, and we're going to go to the same number of decimals that we have here. Okay, so look behind, it's a 404 milliliters per second. So there is our drip rate with the correct propagated uncertainty attached to it. Okay, so let's grow this out and see. Eventually, we want to know how many cubic meters of drip we get per year. So we know that this is 5.6% uncertainty. And really, since all the other values we're going to use along the way don't have uncertainty, they're absolute known values, the number of minutes in an hour is always 60. There's no plus or minus on that. It's just a solid value. Just like pi is pi. There's no uncertainty on pi. So we can just leave this till later, okay? So let's work our way through this problem. So we've got 0.80 milliliters every second. That's going to go for an hour. We've got 3,600 seconds per hour. Okay, we've got 24 hours per day. And we're going to go for a non-leap year, 365 days per year. So what this will give us, our seconds are gone, right? So that's now to hours. Our hours are gone. Now we're into days. Our days are gone, and now we're into years. Milliliters per year once we're done this mathematics here. So you get some massive number like 2, 5, 2, 2, 8, 8, 0, 0 ml per year. Now I'm going to keep all these digits whether or not they're significant because we're not going to do any rounding till the very end. Okay, so we're going to keep all the digits we can till the very, very end. So now we got to take this and we've got to convert it to cubic meters. Water is sold via cubic meter, so we need to know how many cubic meters that is. So probably need a little review here on this, I'm thinking. If you remember, a cubic meter, we'll just draw one here, is literally taking a bunch of meter sticks and making them into a cube. 1 meter per side. So now with that idea, this is also 10 decimeters per side. And it's also 100 centimeters per side. So this can give you all the conversion factors that you need. So 1 times 1 times 1, well, that's 1 meter cubed. 10 times 10 is 100, times 10 is 1,000. It's 1,000 cubic decimeters, and 100 times 100 is 10,000 times 100 is 1,000,000. 1 times 10 to the 6 cubic centimeters. The other thing you can do with this is you can get your liquid measures, which are not really SI. In SI, we just use volume measurements directly. But we know that this is also defined as 1,000 liters. Okay, a cubic meter is 1,000 liters. And if it's 1,000 liters, it's 1,000 times 1,000 milliliters, or 1 times 10 to the 6 milliliters. All right? So the conversion factor you can pull out of there then is that 1 milliliter is equal to 1 cubic centimeter, right? And that 1 cubic decimeter is equal to 1 liter. Very useful to know and really easy to generate for yourself if you just remember a couple of things. Okay? The other, just as an aside, doesn't really play into this, but just as an aside, if this is pure water at 4 degrees Celsius, that also gives you the original definition of the kilogram. Okay, 1 liter of water equals 1 kilogram. Okay, 1 liter of water equals 1 kilogram. So a cubic meter of water will weigh 1,000 kilograms, which we call 1 ton of H2O. That was the original definition. Now the kilogram, of course, is some sort of little lump of metal sitting in France. But that was the original idea, is that you could recreate it from a cubic meter. So that just means we can take this value in milliliters and it instantly becomes cubic centimeters because they are the same thing. So let's start there. 2522 8,800 centimeters cubed every year. And we can go right from cubic centimeters into cubic meters. So 25228800 centimeters cubed per year. I don't know why I wrote it again, but I did. And we know there's 1 times 10 to the 6 cubic centimeters in every cubic meter. Okay? But we realize too that we don't want to this number is going to get smaller, right? When we go from cubic centimeters to cubic meters, and we see that our units don't jive, right? So this is a scenario where you need to invert this value. Okay? So turn all your values that are positive negative and all your positive values to negative values and all your negative values to positive values. So essentially what you're going to do is do a big division here. And you're going to take 6 places off of here, or divide it by 1,000,000 essentially, and you're going to cross off your cubic centimeters, and you'll be in cubic meters per year when you're done. So 3, 6, 25.2388 meters cubed per year. But instead of a 3, it's a 2. I think it's going to go away anyway, though.
Can we just get rid of those zeros because they're insignificant?
Yeah, like so now we look at this, right? And we go back up here and we realize that we only have 2 sig figs in our initial value anyway. So if there's only 2 sig figs there, all this stuff is insignificant. So we get 25 cubic meters per year. And then there's uncertainty on there. We haven't added any uncertainty, so it's still plus or minus 5.6%. All right? So then we can get our actual final value the same way we did before. 5.6 100ths u 1.4. So 25 meters cubed plus or minus 1.4 cubic meters. Now would I leave it like that? Do you think? We're putting too much precision on here. We don't have that much precision on this value. So this then is just going to round to the value on here with the most precision. Okay? So we'll leave it at 25 cubic meters plus or minus 1 cubic meter. Per year. So this uncertainty is just a product of the tools that we used. If we want a smaller value here, we need more precise tools to begin with. So basically what we're doing is we're just we're taking an accounting, I guess, and essentially admitting that our tools can only get us this close to the real value because of the nature of what we used to measure in the first place. Okay? So your first measurements propagate their uncertainty through all subsequent things that you do with your data and your numbers. And it's just an important thing to know in science that this is something that'll be on all your measurements that you ever use from now on in, and make sure that you're just obeying them and obeying sig fig rules. All right, so water costs are 182 per meter cubed. Okay, 182 per meter cubed. So we're going to take, now remember, we want to take our unrounded value, so 25.228. There's a whole, is there any more on there? 8800. And this should be negative. $1.82 per cubic meter. $45.9 $49,916 per year. So it's going to round to 46 plus or minus 5.6% per year. And we'll just put our absolute value and then our range of possible values. 46 plus or minus $2.57. Too much on there. That's going to round up. 46 plus or minus $3. So you're going to be somewhere between $43 to $49 per year. And that's as close as you can get it from the input tools that we use. So somewhere between $43 and $49.